guys did here, but they did. All good. It's all good to go.
Good to go. Okay, welcome. Hello, everybody. My name is Danielle Stein-Fairhurst, and welcome to the Financial Modelling CPA discussion group live hybrid event. So we've got a fantastic turnout today, and we've got even more people joining us online. So thank you for coming along. It's great to do these sessions from time to time. I was very excited recently to hear from David. David Brown is the Associate Professor of Finance in the Eller College of Management at the University of Arizona. I have known him for some time, and when he mentioned that he was coming out to Australia, I jumped at the chance to have him attend a meetup and to talk to us about Monte Carlo simulations. Before we jump into your session, though, I'm going to do the welcome to country. I would like to acknowledge the Gadigal people of the Eora Nation, the traditional custodians of this land, and pay my respects to the elders, both past and present. So welcome everybody, and a very big welcome to you, David, and I'll pass over to you. Thank you.
Fantastic, thank you. All right, I'm going to come out front here because I like to get closer in, and I think that still works. All right, so thank you for the introduction. Today we're going to talk about Monte Carlo modeling, right? Predictive modeling, Monte Carlo, whatever you want to call it. We'll focus on Excel, but we can talk about some other contexts as well. That's all good. All good. All right. So let's get into it by starting kind of run through the agenda of kind of what I want to cover. And as I'm going through this, please stop me with any questions. I'd rather have this be a discussion back and forth, so don't hesitate to stop at all. If you have questions at home, looking online, Danielle will interrupt me as well. So either way is fine with me. All right, so we're going to start out talking about why we should think about using Monte Carlo analysis, like when it's appropriate, what it's for, right? And then I want to talk about how we think about modeling randomness, because that's really one of the most challenging pieces of this, is that to model randomness is hard, right? Because a lot of processes don't follow just a simple normal distribution or a uniform distribution that's not convenient. And that's where a lot of skill and the art behind it takes place. And I'll talk a little bit about that in an academic finance context. But ultimately, it's going to matter whatever your specific context is that you really think about that distribution. So we'll talk about that and why you need to. And then kind of this middle section is let's jump over to Excel. I'm going to show you a simple dice game, right? Something that we can all understand, and start talking about how we functionally go about doing a Monte Carlo analysis, how we model the probability distribution, how we do it both a brute force method, a data table method, and when we might want to go to Visual Basic. And then I'm going to go to kind of how to learn more. And I will say most of the examples I'm going to run through here, I actually have YouTube videos I've built already that kind of go even more in depth than what I'll do here. So if you want to check it out later, that's always an option to kind of review it, work along with it as well. All right, we're good to keep going. Perfect. All right, so why use Monte Carlo analysis? Basically, the idea is that, average outcomes is what we normally model, right? We have some business plan we put together, and you have kind of what you expect the revenue to be, the cost, the sales, and all that stuff, right? But it's often really important to understand the distribution of outcomes. And that's for a couple of reasons, right? We want to sometimes think about best and worst case scenarios. And the reason to do that is really so we can plan for it in our models. All right, so I'm going to talk about that first and then get to the distribution, right? So I think there's a disciplining effect that we get from thinking about best and worst case scenarios, because it forces us to think about how our inputs and parameters are going to change, right? Something we talk about in finance a lot are real options, right? The idea that, say I learned that the demand for my products is really high. Well, what am I going to do? I'm going to build more factories so I can supply more demand, right? That's a real option that I have. So if I get into that best case scenario, I'm going to actually have more capital investment. I'm going to have more widgets I produce, and I'm going to hopefully have more sales as well. But we also want to think about that worst case. What can I do if things end up really poorly? Am I going to sell my assets? And it kind of disciplines the thought process behind the model. Right? So that's one big piece of it. The other big piece is the distribution of outcomes. Right? That's the uncertainty. Right? Stock returns is kind of the big area in finance that I think about this a lot, and understanding, what do returns look like over the next 30 years? Without having some distributional assumptions underneath that and some modeling, it's really hard to conceptualize what returns over the next 30 years are going to look like. And in lots of different contexts, you have to think about what that distribution looks like, and that's where the Monte Carlo analysis comes in. All right, and I already talked about this, right? You're gonna mitigate risk in bad scenarios, leverage up in good scenarios. So I think it does provide that modeling discipline, and I got ahead of myself like I usually do. And hopefully it can help make more realistic projections at the end of the day, right? The distribution helps, but also really that discipline, again, is kind of why I think it's good. And that all depends on these distributional assumptions, right? So I think a caveat is in order here, right? If you have no idea of what the random process looks like behind the data, behind whatever is generating your randomness in your model, by throwing something at it, just saying, hey, I'm going to assume this thing is normal, you could end up actually getting worse information than nothing at all, right? Because if the true distribution, say with stock returns, has fat tails, right? Meaning that bad outcomes are much more likely to happen than a normal distribution suggests, then you build a trading strategy off of this, and oh my gosh, this looks so profitable, we're going to make billions of dollars, let's get all this capital in, and then you have one of those fat tail events happen, well, now the company's going to go under, right? If you haven't modeled for that. So care needs to be taken when doing Monte Carlo analysis to really understand that distribution and to take care in modeling that. All right, so how do we go about modeling that randomness? All right, so here you got to think about what are those most important uncertainties. Right, here are just a couple examples, right? What's going to drive your revenue growth? Stock returns, right? I'll save that kind of to the end to talk about how we think about modeling stock returns over a period of time. Input costs or foreign exchange costs, foreign exchange rates, that can drive a lot of business costs. So those are going to be just some examples of sources of uncertainty, but ultimately it's going to depend on your particular example you're working. Now, how does that uncertainty behave, right? Normal distributions are really convenient, but they don't always fit reality, right? I feel like I'm making this warning enough, but I think it's really important to think about what the distribution looks like, and know that they're hard to work with. Right, this is kind of where the art comes in and where people spend their entire careers, at least with stock returns. Some professors spend their whole career thinking about how to model just the variance of stock returns, right? Never mind the mean itself or the other third and fourth moments, right? So there's a lot of thinking that has to go into that to make it work well.
David, can I
Yes.
just ask that
Yeah.
you
Stand on the side.
Yeah, because
Yeah.
the camera's actually not following you.
Perfect. I can stay here. All right. All right. Now, functionally, how do we do this? All right. Most software is pretty good at generating uniform random numbers, right? Numbers between 0 and 1 that all have equal probability. We can then use those through a cumulative density function. And I'll talk about this and show you an example to translate them in to basically draws from whatever distribution we like, right? We also have things like norm.inverse, where we can actually just directly generate normal random variables as well. But this is what I'm going to show you guys, is that you can take uniform random numbers and generate any distribution you want. Right? So it's a really handy trick to be able to use. Any questions so far? All right, so now this big next section is let's actually get into Excel and look at this stuff and play a game more of this. All right, let's do that. Flip around here. All right, let's get to modeling. Get out of this. Get out of this one too. So here's the game we're going to play. All right, it's a simple dice game. I'm going to actually, let's zoom in and I'll scroll down. All right, so the game is just you take 2 dice, you roll them, and you're going to add that together. All right, so very standard there. We're going to win if the sum of those 2 numbers is between 7 and 12. If, however, it's less than 7 or it's equal to 12, we're going to lose. All right, so we're basically building in a house edge here, right? The casino has an edge. We're going to put it in here as well. We're going to draw if the sum equals 7. All right, so pretty basic dice game. We're going to model this out. And you can imagine modeling this. First, I'm going to model the first random number very simply with the rand between function. All right, so I'll actually type this one out real quick so you guys can see it. I built it ahead of time. But rand between, you basically give it a bottom integer and a top integer, and it gives you a random value between those two. So rand between 1 and 6 gives us 1 roll of a die. All right. We can do that 2 times, right? We get roll 1, roll 2. We add them together, pretty easy. And then I wrote a function here already that you can see. Basically, if it's greater than 7, less than 12, I'm going to give a win. I'm going to report that word. Otherwise, I'm going to report a draw or a lose, depending on the scenario. All right, so I'm just visually showing what the outcome is. Everybody okay with the example? All right, so if that was it, Monte Carlo analysis is pretty easy. You just use rand between and you're set, right? But we don't want to do that. We're going to assume the dice might be weighted. All right, so the casino built it against you, but you're clever and you're going to sneak in some weighted dice. But you don't want to make them too obviously weighted, right? Because then you're going to get kicked out pretty quick. So we'll play with the idea of how much do you weight them and what happens to our expected value. All right, so let's get to that version of the game. All right, so I'm going to set up my model here. Basically, we're going to build the same thing up as before, except now we're going to put a weighting on each of these numbers. All right, so we're going to start out by just putting a little tilt in here. So let's put basically 5% more probability on the numbers 4, 5, and 6. All right, so is that going to work out well for me? If I put more weight on 4, 5, and 6, what do you guys think?
Well, no.
Why not?
Well, hang on. Because it's $2, isn't it?
Yeah.
Yeah, yes, it will.
So it should help, right? I'm a little worried about the 6, right? Because if 6 becomes more likely, well, then 12s are going to become more likely. And I don't win on 12s, but maybe in general, 6s are still good. So this should help me out. All right. So now I have to build up some probabilities for each of these numbers. All right. So this is where the shift comes in. All right. So if we had no shift, we could just do 1/6 and copy that thing down. Right. And everything would have equal probability. And I'm going to go ahead and show you how to build the cumulative density function now before we actually get to putting the weight in. All right. So if you guys remember back into statistics, right, a probability distribution function, or PDF, is this piece here that's giving us the probability of each outcome. The cumulative density function is basically just adding that up as we go. All right. And that's going to let us translate from that uniform distribution into the actual draws of those numbers. All right. So the way we're going to do it is we're going to start out with 0. You can do this other ways. I'm going to like it this way because I get a nice ascending matching, and I'm setting up for an approximate matching technique. All right. And what we're going to do is we're just going to add up everything that came before it. So let's see, we could just do a sum of everything before it. All right. So I'm just doing some of that range, and I'm going to lock this first one. That way, as I copy this down now, we get the sum up before. And you can see what's happened if I click in here. Right? By the last cell, it summed up all the 5 before. And that last one is just, again, accounting for the fact that we're going to do some rounding up. Or sorry, we're going to round down in our method of doing it. So we just need to know that last threshold. All right? So now, again, before I put in the tilt, we can think about generating our random numbers just like before. Right? We're still going to get 1 through 6, but we're not going to use rand between anymore. All right? Instead, we're going to start with the rand function, all right? RAND with the parentheses is going to give us a pure, like a 0, 1 random variable. All right, in this case, we got 0.17. All right, so let's look at that number and see if we can figure out where that goes. All right, so if you rolled a 0.17, well, that's going to land, this is actually kind of a hard example. It lands right between 0.17 and 0.33, right? And so if we thought about taking up the intervals 0 to 1 and kind of chopping it into 6 pieces, it would land in that second bucket between 0.17 and 0.33, which we're going to call that a 2. All right, so now we need a way to map that in. And so this is where our lookup function is going to come in. And I'm just going to do an XLOOKUP. Actually, I can't do that, right? So we'll do an index match because I think this is an older version of Excel. So we're going to index, and we're going to pull back our number. All right, and we're going to match our random value in this lookup array. And it is sorted, we're going to do the less than matching. Because we want the less than value. And we're going to make sure it looks like it works for us. And so it's actually really hard to tell whether it works though, right? Because I can't actually see the random number right now. So let's actually pull that out for a second. So we're going to just make this ran there. And this, I think, is just the practice of always testing your model as best you can to know that it's working. All right, so this is something I encourage my students. Whenever there's a spot where you can check to kind of do a sanity check, is the model working? You always want to take that opportunity because we all make mistakes in building these things. It's just the ability to catch them quickly, I think, separates out more experienced models from less experienced. All right, so if we hit, sorry, function, oh, here we go. All right, so if I refresh the random numbers, there we go. So 0.64, where should that fall? Right, between 0.5 and 0.67, and it's a 4. So it looks like it's working. Let's do just a couple more. All right, 0.35 should translate to a 3. That makes sense. 0.30. I kind of want to get one that shows a 6. There we go. 0.85. It's bigger than anything on there, so it goes into our last bucket, which is that 6. So it looks like our function's working okay. All right, so now I'm going to re-embed the random number in there. RAND. We can get rid of that. And now we should just be able to make 2 copies of this. All right, I wasn't very careful about blocking my cells, so let's just pull that back over. What did I do there?
Probability as well, right?
Oh, all right.
Reference.
Oh, yep, I didn't do either one. There we go. All right, so we got our 2 random numbers. And you build these things in advance, and I set it up for the random number slots, but then I put the things in the wrong spots, so let's just, that's all right. All right, we'll move it over there. We get our total. All right, and now we have our model working, I think. All right, but we haven't put that tilt in. All right, so now how you put that tilt in, really you can model it however you want, where you're going to put it in. What I'm going to do here is I'm going to basically check if this number 1 is in my list of numbers over here. And if it is in the list of numbers, we're going to add 5%, whatever that weighting is. If it's not in the list of numbers, we're going to subtract 5%. All right, so I'm going to do equals a plus if error, or we'll do if is error. And so I'm just doing a match to check, does that number 1 show up in my list over here? So if it doesn't show up in the list, that's where I'm going to get my error message. And I can subtract off my weight. Function of 4. Otherwise, I can add on the weight. Function of 4. Anybody see my problem yet? Yeah, equals back there instead of a plus. And let's see if it worked. All right. It worked so far, but, check your model. What's my problem right now? Probability distribution doesn't add to 1 yet, right? But hopefully when I copy that down, we're okay. So Control Shift. Let's go down. Oops. Sorry, I'm getting used to the keyboard here. There we add back up to 1. Bless you. All right, so our probability distribution adds to 1, and it looks like at least now our distribution function is working. All right, but what is it doing for the actual expected value of the game? Right, because that's kind of what we're thinking about at the beginning. Is like, how much should we weight these dice to make this a fair value game? All right, so that's where our Monte Carlo analysis is going to come in. All right, so let's start out, and we're going to put this weighting back to 0 and see how unfair this game is to start. And the first way I want to show you how to do this is just a brute force method. All right, so we're going to brute force this. And I'm literally going to come down here and just look. Oh, we do have modern Excel. I'm just going to create 1,000 copies of this model. There we go. All right.
Do we get a copy of the spreadsheet?
Yes. I am happy to give, yeah. Yep. And I do have to be careful and go back here now to actually lock these things because copying down did not work. My apologies. So that one we got locked. Let's do this one. We were talking a little bit about Excel esports before we got started, and this is where I'd be nervously sweating because I don't know what did I mess up. All right, there we go. Now we have 1,000 copies of the model built. All right, how practical is it to build 1,000 copies of your model? Right. Normally not practical. Like this is a very simple model, so we're able to do it. So that's what we'll talk about in a second is how do we make this work when we can't make 1,000 copies of something? And I already built some cells over here. Basically, let's assume we bet $1 on this game. All I'm doing is summing up the number of wins, loses, and draws. So we see that we have a few more losses than wins. We had 12 or 25 12s. We lost $4 on this. So our expected value, or the total amount we won or lost divided by the number of times we played, basically 0. All right, so is this a fair game? Do you guys believe that? I get some shakes no. All right, so
draw.
What's that?
What's the draw?
The draw is when you tie. Win, lose, or draw. Maybe that's an American game.
No, but also I thought that you either win or lose in this. I didn't think there was a draw situation.
7. If you're on 7,
is
it's a draw. Yep. All right. So why is it that we're seeing 0? So I did not engineer this ahead of time. This is just basically sampling error, right? When you do 1,000 trials of something, there's going to be variation, right? And that's something we need to know with Monte Carlo analysis is, we're trying to learn about the distribution, or like in this case, we're trying to learn something about the mean, but there's going to be uncertainty around that. And the more trials we run, the bigger the sample gets, the more we actually narrow in that distribution. This is kind of the law of large numbers, if you guys remember that from statistics. But here we have a lot of uncertainty. And I want to show that to you by just refreshing my random numbers. All right, so I'm just going to hit F9 to refresh everything. And we see now 9 cents is the loss on average. All right, if we keep going, we do this a couple times, 3 cents, we're going to get an idea of what the true mean is, but also the distribution of possible outcomes here. So we're not only are we talking about distributions, we're talking about distributions of the distributions, right? And we see, on average, I think it's about 5 or 6 cents. So it's dancing around a little bit. And so now we can think about, well, how can we, what happens with the tilt? All right, so if we add that tilt in, let's see what happens now. And here, this is all caveated with, we're only running 1,000 trials. So this is the amount of uncertainty we're getting, right? Because here, wow, we're making 21 cents now. But let's see how much uncertainty there is around that. So 21, 19, 23. So it looks like it's in the 20s, right? We have a couple samples. So this is probably enough to get you kicked out of this casino pretty quickly. Right? So we probably don't want that much extra weighting to make this a fair game. All right. So before we go to that question, though, let's actually go to our data table. All right. And you've actually seen one of the reasons we're going to go to a data table is that as I'm running this, it actually takes a while when I hit F9. Right? It's actually going through all these calculations. It's basically got, in this case, I have 2,000 random numbers embedded here, right? And that's all of those have to recalculate, and all those formulas have to recalculate every time the spreadsheet recalculates. So it's not a ton of work for Excel to do, but you can imagine with a more complicated model, that would be a lot, and it could really slow your model down. All right, so we want to not make it get slowed down as much. So what I'm going to do here, so let's just switch this back to a 1. And I'm going to get rid of all this just so we speed our model back up. All right, so let's take this. I'm just going to copy it. The other thing I tell my students is always reuse stuff as often as you can. All right, and we got to go back, get the rest of our model here. Actually, just take all of this. All right, it looks like things are working again. But now we want to basically build this so we just have one copy of the model, right? So imagine you have a much bigger model, and now you want to get your data back out as far as what is this total and what is the win, lose, or draw state. All right, so we have 2 things that we want to capture, and we want to do it 1,000 times. Actually, let's stop for a second. Should we do 1,000 times? How do you guys think about how many times you should actually run a Monte Carlo trial? All right, how many simulations should you run?
Depends on what's at stake, but
All right.
I'd go the tens to hundreds of thousands at least.
Yeah. I think it's a great point. The more is at stake, the more you're going to do, right? So you get a better actual understanding of the distribution. When you're starting building things, start with small numbers, right? That way you can test it, make sure things look like they're working. And then if you need to, you go to the supercomputers, right? I have a project I'll talk about at the end here where we did a lot of these stock simulations, and we were doing a million different sets of random numbers. And then we were having to iterate over that thousands and hundreds of thousands of times. And so that's where it's not going to be able to handle on the laptop anymore. And like we use supercomputers at the university to handle that. But you want to test everything first before you go to that investment to scale up like that. All right, so in this case, let's do 10,000 because we had quite a bit of movement there. So let's try 10,000 trials. All right, and what we want to capture here is the total each time, and also whether it's win, lose, or draw. And actually, let me check here real quick. Yep, that's right. All right, so in this first trial, we had a 7 and a draw. All right, who's used data tables before? Actually, as a quick show of hands. All right, a good number. All right, so let me explain data tables very quickly, and then I'm going to talk about how we use them for Monte Carlo analysis. All right, so the idea of data tables, and they're up here in data, what if analysis is somewhere here, there it is, data table. It's basically a way to do a scenario analysis. And I say that, and there's like scenario manager 2 up, but it basically allows you to change a parameter and see what happens in your model as a result. All right, so typically you could, let's see, let me just show you. That'll be an easy way to do it. So for example, say I want to know what the probability of a 1 looks like, all right, based on the weighting. All right, so I'm going to put a weighting here, and that's fine. And then I'm going to run my weights from 0.01, and we're going to increment them up by 0.01. All right, so we're just going to see what the probability of a 1 looks like, and let's capture that as we change that weight. All right, so if you haven't seen a data table before, what I'm going to do here is I'm going to hit Alt-AWT, that's our shortcut, and you have 2 different inputs here, either a row input or a column input. Those are so you can do 2-dimensional data tables. We're just going to stick with 1-dimensional here. And what you need to know is that the column input cell, in the column down here, this 1 to 5, is where basically our input variable is. That's what we want the weighting to be, because it's in a column. We're going to put that column input cell up here in the weight. All right, so what it's going to do, and I'm going to come in front here so I can point at this easily for you guys. All right, so what it's going to do is it's going to take this 0.01, it's going to put it in this cell, and then it's going to take whatever value is in this cell, basically copy paste values and put it right there. All right, it's then going to take this value, 0.02, put it up here, copy paste values of this, and put it there. And so it's basically just going to record what your model gives you, whatever you're putting in this cell, across those different input parameters. Switch back around. We say OK. It didn't work. What happened? Either I messed something up, or often what happens is if your formulas are set up, a lot of times they're set up as automatic except for data tables. All right, why is that? It's because when you're running Monte Carlo analysis and you have all these random numbers calculate whenever it runs, that can really slow your spreadsheet down. All right, so all we got to do is hit F9 to calculate now, and now we can see how those weights change as a function of changing the input parameter of that weighting number. All right, so that's data tables traditionally used. All right, so now how can we use this to do a Monte Carlo simulation? All right, so let's go back up here. So we're going to do the same thing as we did before. I'm going to do this one way first. See, Control Shift down, there we go. Alt-AWT. And so notice that my trials are in the column, right? So I'm going to use the column input cell. And now the question is when I do a trial, what do I need to change each time? Right? In the past, I was changing my weighting input. But I don't necessarily want to change the weighting input each time. What do I want to change?
Nothing.
Nothing in the model except for the random numbers, right? So what I'm going to do is I'm just going to pick a cell that's not being used. So I3 looks really good. And so what it's going to do is it's going to go in here, through again, and it's going to take the 1 and it's going to put it in that cell. Right? When it puts a 1 in there, that forces anything that's volatile, the volatile functions in Excel to recalculate. Random numbers are one of those. So it's going to force the random numbers that are hidden back here to recalculate so our answer updates, and it copy paste that answer down. Right? And then it's going to go to the 2, and it's going to put a 2 up here. Forces the whole spreadsheet to recalculate with the random numbers, puts our new answer there. So we're basically tricking Excel, and I think it's not tricking because I think they intended on this, to generate our 10,000 Monte Carlo charts. All right, so let's see that happen. All right, we say OK. Didn't update, right? Because it hasn't actually calculated it, so F9. Now we have our 10,000 trials. All right, so I want to show you one thing about data tables here, though, is that right now I just calculated the roll value, all right? What if you went and did another data table for the win, lose, or draw? All right, so say you made 2 data tables side by side. If you did that, the random numbers aren't necessarily going to be the same between the 2. And so the results aren't going to line up effectively. All right, we don't want that. You want to kind of have a consistent output. And so what I'm going to do is I'm going to create a 2-column data table. And I want to make this distinction that it's not a 2-way data table. All right, if you've done 2-way data tables where you use both a row input and a column input, well, then you're going to have 2 variables changing at the same time. It looks like we have that since we have 2 columns or 2 columns set up, but really we're just capturing 2 different values here. So we're still going to treat it like a 1-way data table with a column input cell. Say OK, F9 to refresh, and now we've got our values. And let's see if it's actually working for us. Well, in this case, it looks like it's working. It's about the same expected value, but I'm actually currently not using all of our trials. Right? We have 10,000 trials we made. I'm going to come in here and just add a 0 to a couple of these things. That way we make use of the fact that we built a data table a little bit bigger. And our winning decline and our expected value, we got to divide by the count. All right, so 20 cents. So now we have a more powerful Monte Carlo, essentially. We have more numbers. It's a little bit streamlined for Excel because now we also have the data table running it. And now let's actually play with our question that we had, right? What's the right tilting to kind of get this thing close to an expected value of 0? All right, so 0.05 is too much. Let's try 0.02. All right, we hit F9. That's down to 4 cents. But also we still have sampling error, right? So let's hit F9 again. 6 cents. 5 cents. So you notice with 10,000 trials, it's still moving around, but it's not moving around nearly as much. All right, so we can start to narrow in on it a little bit. So let's try 0.01. What does that do? All right, now it's 0 the first try, so maybe we're onto something. A little bit positive, a little bit positive, a little bit negative. So it's kind of dancing around there. It's looking like it's close to fair. All right, so what do we do if the stakes are high? Right, if this really has to be right and we got to figure out this weighting precisely, we're going to do a lot more trials, right? We can stick in Excel and we can do 1 million trials if we want, right? We have 1 million rows to work with. If we needed to, we could figure out ways to do even more than that. Typically, when I need to do things at scale, I'm going to something outside of Excel, but Excel has had a lot of tools developed in the last couple of years that you could handle it there if you want to. It's just, I don't think our supercomputers are set to handle multiple instances of Excel, whereas MATLAB is pretty well built for that. All right, let me pause for a second to take a drink and let you think of questions. No questions? All right, fair enough.
Yes, there is one that's just popped up online.
Great.
We have a question from Justin. Would we be able to incorporate multiple independent variables or drivers based on Monte Carlo analysis in Excel?
Yes, you can put as much randomness into the system as you want. It's going to be a lot harder to know what's driving it, though, right? So as you put more inputs in that are going to be random, you're going to have some ending answer that you're looking to see what it is, or maybe you have multiple outputs you're looking at, but it's going to be harder to delineate where that's coming from.
Yeah,
And
typically you would just sort of test one input, wouldn't you? Say how sensitive is the model to this one variable? But like you say, when you start putting multiple, I mean, you can, but
Right.
yeah, it makes it harder to analyze.
yeah, well, I mean, so the example I'll talk about in a minute from my research is one where we were looking at tax uncertainty as well as stock return uncertainty. And it had to do with whether you save in pre-tax versus post-tax vehicles, which I hear is something that's being debated here a little bit right now. But in that case, we had two different sources of uncertainty. They're interacting. And when you build the model, though, you want to build it so you know it's working in one dimension and independently working in the other dimension before you start putting them together, right? Again, checking the model as much as you can at points where you kind of know what answers to expect. And that's when you can actually start to learn things from it, when you find out how do these things interact. So definitely can do it. It just gets a little harder to do. All right. So the last thing I want to bring up, and I want to leave some time to have more questions and talk about some of that other modeling, is going to VBA. All right, so let me zoom out a little bit here. So why might you want to go to VBA? All right, so VBA, Visual Basic. For most Monte Carlo, if you only have one source of uncertainty, then it's not a big deal to do it like the data table we just did. But one thing you might care about if you're going to go to the casino and actually implement this strategy is, what do your returns look like night after night after night, right? You can't go to the casino and play 100,000 rounds of this game in one night, right? So the sampling variation matters. So in that case, you might want to think, all right, well, I can go pay 500 hands a night. And so I want to know, what's my worst night going to look like versus my best night? All right, so now we have multiple levels of uncertainty because we have, 500 trials for a night, but then we have multiple nights and we want to run that multiple times. All right, so that's where VBA can come in. And VBA, more or less, in this example I have, and again, you guys can have the spreadsheet afterwards, is a glorified copy-paste tool, right? So think about back here with method 2 on the data table, right? This summary output of what happened in the game is what we'd want to capture 1 version, 2 versions, 3 versions, 4 versions, and build out across and really kind of analyze what happens at that level. All right. So it's that second layer, again, of uncertainty. And that's all that's happening here is I'm kind of, well, actually, I show it both ways because you can actually code all of this in VBA directly, right? Anything that you can do in an Excel spreadsheet, you can pretty much code up in a language, right? It's just a little harder conceptually. You can't see it laid out as nicely, right? But that ability to kind of repeat that second level of uncertainty, I think, is the real key and what's nice about using VBA on top of this. I don't feel like I want to get out the VBA code unless there's a huge amount of demand for it, because I think that's something you can dig into later. And actually, I do have all the videos that walk through exactly how I do the VBA and how I build it up, if you guys want to check that out on YouTube later.
I'm interested in VBA.
How many rows is it? How many rows of code?
Probably like 50.
50 lines of code.
50.
Can we see? Just
Oh, yeah. Hold on. We can. I didn't anticipate well, so we got to go in and add our developer ribbon, right? So if you haven't done much VBA before, the first thing you do is enable this developer ribbon. We'll get into that. Developer. So that bit of code will basically build it for you. And so that's the copy paste code, right? If you just want to take a model and copy paste it, you could do this section. And if I actually go down.
Oh, because it's using formulas in the spreadsheet, is that?
Right, it's using formulas in the spreadsheet. But I think your question was more, what if you just build it all in there? And that is this version. So in here, I'm basically building up the random numbers, right? R&D is the way we do that here. I'm using some match functions. Ooh, and I actually lied. I didn't do it all in VBA. I actually took my distribution function from the spreadsheet. So I still pulled that in.
Okay.
So that was the only thing I pulled in, but all the other calculations, right? This is basically our if statement for win, lose, or draw, right? So that's where that's all happening, and then it's outputting it here down below. So you can look at a couple of these different ways to do it. when I send the spreadsheet afterwards, or when Danielle sends the spreadsheet afterwards. Good question. Any other questions there?
Was Donald Trump a random event?
Yeah, well, no comments.
That's what I thought. Sorry, Eric, I tried.
Yeah. All right. So that's kind of the Excel walkthrough. Let's actually jump back. I'm going to save that one. Get back here. I can get back from out behind the computer for a minute. All right. So how to learn more. So I already said this a little bit, but here are a couple different links you guys can look at for getting more into this. If you want to get started in VBA, I have a lot of just intro to VBA stuff as well on there. Basically, I flipped my financial modeling class. If you guys know what a flipped classroom is, basically my students all watch videos before class, and then they come in and we work through exercises together. So there's kind of more one-on-one interaction time in the classroom. But that means all my videos are basically up on YouTube. So if you guys want to see my class and how I put that together, it's up there. In particular,
I might pop that onto the email when I send the email out to everyone. So those of you who are in the room, if you haven't put your email address down, make sure you do, and I'll send out a copy of this together with the recording.
fantastic. And then there's also the Monte Carlo. It's a playlist in itself, which is more of what we've been talking about tonight. But there's also lots of other stuff on there. And I actually do want to talk for a minute about something else I've started. Kind of one of my passion projects is the Microsoft Excel Collegiate Challenge. And there's the link to it. But I'm going to fast forward to our picture here, and this is kind of like the banner you see on our website. What this image is, it's actually last December, so December 3rd last year, we had the first live Excel esports event ever. It was students competing. They competed for a $30,000 prize fund, so big stakes. Isaac Lee here won $10,000. He's from the National University of Singapore. So he flew over, made the trip. We had a team of 3 from Madagascar, travel like 3 days to get to the competition. But it was a fantastic event because we're seeing young people get involved with Excel, with financial modeling at earlier ages, and giving them opportunity to really engage with this material. And what I'm doing with it this year, and it's not just me, it's a whole team. If you guys know the Financial Modeling World Cup, they're the partners in this, so they're driving a lot of this forward. But what we're trying to do now is just engage more students. All right, and part of that is that we have a whole year-long program going now, where each month challenges come out for the students to work on. So in April, the challenge was a keyboarding game. All right, so I don't know if you guys have ever tried one of these, but basically it's a kind of a track that you go down, and as you go down the track, you have to do different shortcuts. But you don't have to, but to get a good time, you want to learn how to do the shortcuts. That way you get efficient with the keyboard, and you learn to move around Excel quickly and
Is
efficiently.
that the one that Jim Early put on YouTube the other day?
Yes.
That's pretty cool. Did you see it?
So Darren Early, Dim will go through these and
He's like a world one of the world champion financial modelers.
yeah, he's who puts fear into my heart.
Yeah.
And we're going to battle in just a couple days. So really in my career, I just want to beat Dim once. Right? That'll make my day. Anyway, so it's a keyboarding exercise where you go through and just encourage you to learn shortcuts to get more efficient. The May challenge is going to be about learning functions like filter, sum ifs, different functions that are useful that we apply in our modeling, but for students, it's a way to introduce it in kind of a fun setting. All right. So to the extent that you guys are in the established world of Excel, if you have a relationship with your university and you know somebody there still, and you can help me get in contact with the professors or career staff or recruiters at your university, I would love to talk to them to get their students involved. Because one thing I've found is, we can advertise online, we can have people like me post videos about it, but ultimately students listen to their professors. So we're kind of trying really hard this year to engage professors at universities. So to the extent you can help us make those connections, I'd really appreciate it. Feel free to reach out. My bio has my email address, but I think it'll also be on things that Danielle sent out. So feel free to reach out as far as that goes, because we're really just trying to get more students. Any questions about it?
Yeah, so I've got a question in what we were talking about before this. You said you had some YouTube videos.
Yeah.
Are they just beginners VBA videos, or are they all different levels?
I don't go that advanced. Basically, building through Monte Carlo is as far as I take my students in class.
Okay.
So not advanced topics. So it starts from the extreme basics of like, what are the different windows? let's build a hello world program. It's kind of the classic first one.
Yeah.
So it starts nice and early and kind of gets through building the code I showed you a minute ago.
Okay, yeah, thank you.
Yeah, good question. All right, so before we can get into questions, but also let's talk about actually modeling stock returns, because I said I talked about that as well, and different ways we can think about doing that. So let me switch over here for a second. Get rid of that. All right, so I'm not gonna go through the entirety of what this paper was. I gotta stop that. Okay, there we go. It's showing. Okay, so basically what this paper was doing, I'll give you a quick synopsis, is asking how you should take into account uncertainty in tax rates when you're making investment decisions and saving decisions for the future. In particular, how do you save a pre-tax versus post-tax account? All right, so how does that tax uncertainty matter? So we had to model two different sources of uncertainty here. So one are taxes and stock returns. All right, so tax rates, we know basically, we basically made some big assumptions here. And these are kind of based on US tax code, so the details aren't important. But what is important is how we modeled it. All right, and I'm actually going to rewind a bunch here. I got a good figure for this. Here's the figure. All right, this is what tax rate changes look like in the US from basically 1914 when federal income taxes started up through about mid 2010s. All right, and so what we've graphed is the top tax rate is red, and then what taxes would have been for a $250,000, $100,000, or $50,000 income. Right, and so you can see all these tax moves that have happened over time. You know, these big moves, World War I, World War II caused big spikes in taxes, and then we see lots of other movement throughout the 50s, 60s, and 70s. Some big drops, these would be like Bush-era tax cuts, and then subsequent increases. But basically, you have lots of movement in taxes, right? So how should we think about modeling taxes into the future, right? Thinking 30 years out. It's not a straightforward thing to answer, right? What we decided to do is is use this empirical distribution, right? If we think about an empirical distribution, that's what actually happened to model future changes. So the idea is we'll just draw one of these years. So imagine a uniform distribution, right? Where you can get any one of these outcomes with equal probability. All right, so if I'm thinking about next year's tax rates, I can start wherever I am today and say, well, what was the tax rate change that happened in 1960? Maybe that's the year I drew. And then from there I say, well, let's take another year, maybe 1950. And so you draw 30 years from this random distribution, stack them together, and that's how you could project forward, what do we think tax rates are going to look like in 30 years, right? But then obviously there's going to be some distribution over that. So let's see what that looks like. Here again, I'm fast forwarding. All right, so here's what those distributions look like, right? And this is kind of what we're trying to get at with Monte Carlo analysis. Is we start out here, so this would be like a 10-year horizon. So you're close to retirement and you're at the low income rate, right? So you're in the low income tax bracket. You know, you can be somewhere between 0 and about 40%, with the center around that 20% mark, right? So some uncertainty, but not a lot. Whereas at the high tax rates, at the high incomes, much more uncertainty. And that's because essentially at higher income levels, tax uncertainty is much higher. There's just been a lot more volatility in the past. And so that's what we see in our distributions here. If you go down and actually look at 30-year horizons, everything spreads out a lot more because there's a lot more time for things to move around, right? So more tax uncertainty. So that was how we used kind of the empirical distribution there to model that, right? Any questions on how we kind of drew from that past distribution? If you've heard the term bootstrapping, that's kind of the idea there, is that we're bootstrapping from the actual distribution of outcomes.
David?
Yeah.
Sorry. How would you then bootstrap it between the 10 and 30 year?
So it's basically just whether we're going to draw 10 years of changes or 30 years. So we did these independently.
Okay. And you were not trying to do some interpolation in between?
No, we're not trying to. What we were trying to do in the paper is demonstrate this is kind of a policy for someone close to retirement versus someone a long ways away. All right, so now what do we do with returns? All right, so here we can basically, again, bootstrap from the empirical distribution. So we're going to draw randomly returns from July 1926 to June 2015. All right, so you can imagine a scenario. We're gonna assume independence from tax rates, and you can imagine a scenario where you just draw one monthly return at a time, right? And if you want to do 30 years, you stack up 12 times 30, right? 360 different months of returns, right? Let's see that. And I'd say we solve this with a million sample paths. Does it seem like a good idea to draw months independently? What do you guys know about stock markets? What happened in March 2020? Right back down. What happened in April 2020? Right back up, right? We've had this happen a lot of times through history. We see pretty big mean reversion, where there's dependence in returns, that we have patterns that take place, over more than a month. Right? So how would you handle that? Right, this is kind of the next level of bootstrapping. So what we did in this paper is we essentially did something called block bootstrapping. Right? So the first thing we would do is draw a random number, something between, I think, 3 and 15 or so, basically, or 3 and 60. That's the size of the block. All right, so 3 months would be the smallest block we would draw. 5 years would be the biggest block. So we'd say, all right, randomly, how big is the block? And then we would draw a section of those returns of that length. All right, so you're basically taking out blocks that preserves the correlation of returns across time in your random distribution. Right? Because if we would have just done simple monthly draws, we're not going to have that pattern of correlation over time that we know exists in the data. So this is something people before me kind of figured out, that this is a better way to model long-term stock returns. And so that's kind of my initial point about really understanding how to model those returns is important to getting good answers from your Monte Carlo analysis. All right. So I think that is most of what I wanted to cover. So how are we doing on time? All right, so students are always happy when I finish a few minutes early. And now you can fill up the time with questions. So what else can I answer? Yeah?
So random function, it's not totally random, is it?
That's true.
Do you sometimes adjust or do some further modeling around that?
No, so what the question is alluding to is that I think that random numbers in anything is not truly random, right?
Yeah, that's exactly right.
So that is beyond my level of computer science knowledge. So I have never worried about it essentially. I will say one thing I do, and this is actually I think important for modeling, is you want repeatability in your model, right? So you want to be able to have the model run and get that distribution out the same way every time. That way you know something's not breaking in your code. And so this is almost where like seeding a random number is one thing we call it. So you basically put a seed in, that way it's the same set of million random numbers you use every time. Functionally, the way I've also done it, and the way I do it in my class, so I'm making sure my students get the right answer, is just generate a set of random numbers and save it, and then just use that set of random numbers. So on tests, I give students a pre-generated set, that way everybody gets the same answer out. But I have not worried about the lack of true randomness in the underlying distribution, and I don't know more about that.
This paper you mentioned.
Yeah.
Published paper?
Yeah.
Yeah, because I'd be curious to recreate some of that if the mechanics of how it was done is laid out.
Yeah.
Is it how I get that?
Send me an email.
You got it.
It's in the Journal of Financial Economics from 2017, I think. But yeah, happy to send it to you.
Thanks.
Yeah. Good questions.
I looked at that tax, raising taxes. I think to myself about how little tax is paid in America now, according to that. That's probably why America's such a deficit.
So I'm not going to say no comments on that. I totally agree. Yeah, I'll go back to the graph so you guys can see. Right, so this the historical taxes. I mean, it's lower now than it is then.
Yeah.
Right, Trump era taxes cuts moved
Trickle down is nonsense. It's not a theory, it's a mantra.
I agree. But yeah, I mean, if you're thinking about retirement planning, you're looking at this distribution of taxes, like odds are it's got to go up at some point. How long can we print trillion dollar coins if we're going to do that in the next few weeks? Who knows? But yeah, I think we're going to have to eventually start raising those things. And You know, I guess an important thing of modeling, right, is that we did not want to build that into the paper. Right? We want to kind of stay agnostic to, where is this thing going to go in the future? We're going to let the distribution speak for itself. I do think taxes are going to drift up over time, which makes locking in your tax rate today with kind of post-tax savings all the better. But that's not something we wanted to bake in. And I think that's the same thing when we're doing modeling, right? You don't want your own biases and opinions to get into the model. You want to lay your assumptions out as clearly as possible. And if somebody else wants to change them and make that adjustment, go for it. But you want to build the model flexibly so the model doesn't have that built in. Other questions or thoughts? Anything else from the chat?
No, we all good.
Yeah.
What do you see the future of financial modeling in terms of the application of open source programming, Python? You mentioned Matplotlib. I understand that's quite a popular language in universities. Like I totally get the benefits of Excel. It's all in front of you. You can visualize things and understand how numbers are interacting. But yeah.
Python, MATLAB, etc., and knowing how those tools can work for when to use them. So that all said, I'm going to caveat that all, because the Excel team has been working super hard for the last few years to make it so you can do so much of this stuff in Excel that you couldn't before. I don't use Excel as like a power user like that to where you're handling huge amounts of data. But I mean, they basically built SQL into Excel via the Power Query function, right? And Power BI does all the visualization stuff. So kind of the whole suite can handle a lot of stuff that people have had to go to other softwares in the past for. So in a sense, it's almost a race of the Excel development team. Because also, I mean, they're putting ChatGPT into Excel, right? They're a big OpenAI investor, so I think they're going to be on the cutting edge of incorporating these tools together. So yeah, I always encourage my students, the more you learn these new tools, the better though. So I don't know if that's a straight answer or not for you.
It's open. Yeah.
Yeah, very.
Have you done videos on ChatGPT?
I have not. No, and actually, so dirty little secret, I have not been able to get ChatGPT to work. Every time I've logged on to try something, it's always too busy and it doesn't work.
In Australia, if you do it in the morning, it's actually pretty good because nobody else in the world does it.
All right, I'll make a note for tomorrow morning.
Yeah, you can usually get on in the morning in Australia.
Yeah, I was teaching a class on modeling kind of markets when I was at Tennessee, the University of Tennessee earlier this year. And somebody told me that they were able to take a lot of what I did in the lecture as far as how to code up this model that we were working with. And ChatGPT gave them most of the code to do it, which, more power to ChatGPT. Like if it saves our time in building kind of the simple things, then we can spend more time thinking about the harder problems and making variations to it and editing the code. Yeah.
Before we do the modeling, we need to collect data, right?
Yeah.
So the data actually is a longer time is better. Let's say it's new companies, how do we apply it onto the sport, like to a new company, like 2 or 3 years, or even sometimes just few months time?
Yeah.
Yeah, it would be very difficult, isn't it?
Yeah, and there's a lot of uncertainty in the assumptions under that distribution, right? And I think this is always a problem with like entrepreneurial finance and startup financing. And I think a lot of times what you're going to rely on other companies that have come before in the space in similar positions, similar kind of stages of development to give you an idea of that uncertainty. And I think that's where, venture capitalists and those types of investors and their experience is going to actually be very valuable.
That's right, it's a simulation analysis, isn't it? Using the other company to, in a way, or multiple companies put together to form a model.
well, not necessarily to form the model, but to understand how much uncertainty there is, or what that uncertainty looks like.
Yeah.
Right. And I mean, really, a lot of times when you're doing these models of early stage companies, it's usually not a distribution they're interested in as much as the scenarios. Right. Worst case, middle case, best case, and maybe more gradations between those. But I think for the most part, let's think about what happens in those couple of different states of the world, and they're not as worried about the distributions. That's just been my impression. Yeah,
That's true. That would be the second stage of analysis. I believe that from the beginning will be more specific, narrow it down, and do our analysis. So in that case, in terms of mortality analysis, may not be useful. It's in the early stage of that.
yeah. Because that distribution is going to be so uncertain and hard to pin down, I wouldn't trust it that much.
Yeah, that's true, isn't it? Won't
Yeah.
trust this word.
Yeah, exactly.
Thank you.
From memory, Monte Carlo simulation goes back to the 1940s. They're trying to develop a theoretical atomic bomb. They needed to be able to calculate the probabilities. Has it advanced since then, or are we still using, is there a future version of something that's better than Monte Carlo simulation?
Fundamentally, I don't think so. I think what we've gotten much better at is understanding the distributions.
Yeah.
Right. That's where the hard work gets done. Right. And that's where it's hard for entrepreneurial firms with stock returns. Again, like I said, tons of people have spent lots of time modeling those. And I'm sure, I mean, the physicists at various places around the world are spending lots of time modeling, I can't talk about the different types of particles because I don't know that well, but modeling the physics. Right. So I think the distributions is really where the understanding comes in. And that's pulling data from the real world and understanding, what data generating process could have given rise to this set of data. And the problem with that is it's always moving, right? Maybe not in physics, but in finance, we always have to think about, is the fundamental data generating process that's giving rise to stock returns, is it the same process today as it was 20 years ago?
Yeah.
And often, I mean, the amount of changes that have happened in markets, as an example, make me think, no, it's not the same data generating process. Is it close enough? Maybe for certain things. But again, that's where the art kind of comes in, making judgment calls of, can we use that still, or should we maybe put more weight on more recent data? So that, yeah, it's the hard problem, and I think it's going to be with us for a long time.
So David, a question to come to, you just mentioned that. So in other words, we should understand the behavior of the data before we build a model. Is it correct?
Yeah, I think that's a good way to put it.
Yeah, if you don't understand the behavior of the data, right, how behave for information. So you build a model can be incorrect. Is that
right? Yeah. If you don't understand the behavior of the data and the underlying uncertainty, then the model's going to be junk.
Yes, right.
And that's why I like to build models with dice rolls, because I know for the most part how those work.
Yes.
Right? Provided it's actually properly weighted, though. Right. So that's another question. Right. You get into these questions with data generation of, say I see that, that dice game is turning out favorably for me. How much do I know, when do I know that the dice are likely to be weighted or not, right? Because there's a certain amount of randomness in things, but at some point also there's likely to be some weighting. So there's a lot of people actually will study that and how do you detect whether things are truly random or not at some level.
Yeah.
I think we might need to leave it there.
Perfect.
Thank you so much for a wonderful presentation, and thank you everyone who has attended. It's been lovely to see you, and yeah.
Thank you all very much for all the questions. I really appreciate it.